Okay. Hello, my name is Nikola Marincic. I'm a senior postdoctoral researcher at the chair of CAD. I will be replacing Ludger Hofstadt today for this lecture. And he asked me to teach you something completely different, something you might not have expected. It has to do with mathematics, and it has to do with mathematics which has to do with machine learning. So the mathematics which is kind of the basis of machine learning and computer science. So in a way, this could be a question of whether this has something to do with architecture and whether it does not. In one sense, it doesn't. It is mathematics. On another side, I really do not expect to see architecture staying the same as it's today with all the advances in machine learning. And recently I've been traveling to China, and I was driving to 250 kilometers through the Shanghai area. And during these 250 kilometers, there were all new buildings, one next to another, on both sides of the train. And then you realize that in some parts of the world, there is simply no time to design each individual building. So some parts needs to be automated. On the other side, you have companies like Google who are trying to simply kill any expertise with their machine learning algorithms and try to kind of create the most generic basic products of architecture or the other engineering disciplines, so they can profit from them, so that somehow they might be taking your job. They will be competing with your jobs in the future, and your job as an architect is to stay above this. But I think for you to stay above this, you cannot not care about what's going on with machine intelligence and machine learning. So for this reason, I think it's good to learn some basics which can be then later used if you would like to learn further. If you would like to learn further, I'm giving a course called an Introduction to Machine Intelligence for Architects and Other Non-Engineers. It's offered as a Alpha, and I started with 90 students. Now it's around 50. But I think it still might be interesting for you. So there is a couple of ways you can follow this course. You can just take notes or do whatever. Or if you would like to kind of have notes and run them in front of you in code, then there is a way how you can do this. So if you would like to follow, then please open this URL in your computer. And then if you do that, you would land to, let me do that. You will land on this page, which is my course notes for this course. And the lectures I will be teaching today are these two, Introduction to Vectors and Introduction to Matrices, because this is an important part of defining what a neural network is, for example. And you can just open them, for example, if you just want to read the course notes. You can see it here, so you can follow on your own. Or if you would like to, there is some code here, as you can see. It's a Python code. If you would like to run that code, you can do this. You can go to Google Colab, or just type Google Colab in your browser. And then take this link here. Copy it, paste it here. See here, go to GitHub, because my code is hosted at GitHub. It is a place where code is being shared for free and collaborated. And then you can open, for example, Introduction to Vectors. And what Google will do is it will recreate my code in their own software. And then you can, for example, run this code. You can import this library without having to install anything. It will ask you whether you will run it anyway or not, because it's not written by Google. If you say yes, Google will create a computer for you, a virtual one, in the cloud. Now it's set connected. It has memory and storage, and then you can run the code. If you're interested. If not, it doesn't matter. You can just follow what I'm doing. Okay, I will be doing this whole thing on my own course notes. So And because there is no large enough blackboard, I will also be trying to draw some sketches on this screen, which is not perfect, but yeah, that's what we have. And today's idea is to cover linear algebra, which is enough to understand what machine learning is about. So the idea is that if you want to learn go to a machine learning course, they will tell you, oh, you need to take 3 semesters of mathematics, you need statistics, you need derivatives, you need linear algebra, you need like 3, 4, 5 semesters, depending on the offered course. You need to master all that so that you can learn about machine learning. What I will try to do is to compress a whole semester of linear algebra in just these 1.5 hours. And I hope I will try to really put out points in a way that architects might understand them. So thinking more about space and the realization of linear algebra into space. And I hope that you will find it interesting. So the idea is that there are different kind of quantities that we are in general dealing with. And some of them are called scalars, so these are numbers. So you can say, I make 1, 2, 3 steps, so I can count, or I can measure. For example, something is 1.5 meters long, or I can say there is a number called pi, which is the circle's circumference correlated with circle's diameter. So numbers can have many uses. Then there are some kind of different kind of structures, different kind of quantities, not quantities, different kind of, yeah, let's call them structures for now, which offer more than that. And for example, if I go here, and imagine now that I'm drawing a plan, so this is some kind of village, there are some roads, and then there is some lake here, it doesn't matter. And imagine that we have 2 people here, one is here, person A, and here is person B. And now imagine that this person would like to walk for 20 meters. How would you represent where this person might walk? So this person wants to walk exactly 20 meters. How would you represent it here in terms of these 2 points? One idea would be to say, that's a circle. Yeah, I can draw a circle. Yeah, and the diameter of this circle is 30 meters, for example, 20 meters. Yeah. But what I'm missing from this perspective, what I'm missing is, so this is definitely a quantity. This is called a scalar, and it's 20 meters. But it doesn't tell us, in this case, where we want to go. It gives us an option to go anywhere with 20 meters. So if we want to be a little bit more specific about where we want to go, we need to define another thing, which is a direction. For example, this person might want to go there. This person might want to go here. So vectors are things which not only define what is the quantity, for example 20 meters, but also point into a certain direction. But as you can see, these vectors here, they can be moved around the space. So they're not at fixed location in space. For example, this vector, this person B might decide to go in the exact same direction here. Then you can say, okay, they have the same direction and same distance, but they are at different places of space. So what can we do then? How can we then talk about vectors like we talk about numbers? When are 2 vectors equal, when they're not? So the interesting thing, what we can do, and what linear algebra does, is connects algebra, so in arithmetics, so dealing with numbers, connects it with geometry. So if we took these 2 vectors, or any number of vectors, and we took the tail of the vector, so this part here, and fixed them to the coordinate origin, then something else happens. So then all vectors start at the same place, and then we can see where does their tip point, for example here, or here, and where does the tip point, we can measure this according to these two coordinate axes. And you can see what we get is coordinates. And then we can see if two vectors are equal, if we put them in the coordinate origin, they should point to the same place. Which means two vectors will be equal if they have the same coordinates. Okay, the same thing happens in 3D, as you can see here. We simply add another dimension. And then we have three numbers representing it. This is x coordinate, y coordinate, z coordinate. So the thing about linear algebra, what is interesting about it, is that we can define a 2D vector like this. So this is in 2D space. And then we can do 2, 3, 5 in 3D space. But what linear algebra really asks is, what happens when we go beyond that? If this is the representation that we have for 2D, for 3D, what happens if we have 2, 4, 6, 7, 8? So what this actually means is that this is now a vector in 5-dimensional space. Problem is, we cannot see 5-dimensional space. We do not have senses to see what is a 5-dimensional space. But we can have now numbers as our intuition to understand what is going on around. What is important about these vectors is that this will be first dimension, second dimension, third, fourth, fifth, which means that they must be ordered. So they are represented as an ordered list of numbers. Okay? And in this way, we can start thinking in other ways about higher dimensional spaces in terms of numbers. And then if you want to represent vectors, there are certain conventions which we usually use, and you will later see why this is useful. And usually how we represent vectors is with this kind of square brackets. So we take a vector, we put an arrow on top, and then in square brackets we put first coordinate, second coordinate, first coordinate, second coordinate, and you can see this is x, y, z, x, y, x, y, x, y, x, y. Yeah? That's kind of straightforward. And now, if we would like to do the same thing in Python programming language, I know you're working with Mathematica, but I'm working with Python, so when Ludger asked me, I simply couldn't so quickly change everything to Mathematica, although I think it should not be very complicated. So the idea is that you import some kind of library for vectors. It's called NumPy, and then you call it MP. And then you say, define vector by something which is called MP array. And this is how you do it. If you have a vector 3, 4, you just use these brackets to define it so that it's a vertical vector. And then you just, if I run this code here, these 5 vectors are now stored in this variable. So A, B, C, D, E. They're stored there. Yeah? And now there's a command in Python called print, where you can just see what is the value of a certain variable. So if I say print A, you get 3 and 4, just like here. If I say print E, you get 2, 3, 5. If I say print D, you get, oops. If I say print D, you get D, yeah? So quite simple. I'm going to start this class as starting with very basic and even banal principles, but then we will go to something more abstract. So bear with me. So now when we did this, when we defined vectors as coordinates, what we in principle miss is the length. So when we say what the coordinates are, we do not know what the length of the vector is, yeah? Because we concentrate now where the tip lands. You see, there are two perspectives. One is that you walk and you measure how much you walk, and one is that you set a target in space, and then you need to go to this target. So, but the interesting thing is, just take this vector A, for example, and if we put it here, you see that it's not really difficult to compute what would be the vector's length. So, for example, if I go here, if I take this vector, what it is, 3, 4, oops. 1, 2, 3, 1, 2, 3, 4. Yeah, if I draw this vector, you can realize that this is actually a triangle, that this is 4, this is 3, this is 4, and then you can say, yeah, of course, this is, for example, c squared equals 3 squared plus 4 squared, so just Pythagorean theorem, so c squared equals 9 plus 16, c squared equals 25, and c is equal to 5. And then you can say, okay, nice, I know my length. Again, this is great for 2D and you think this is geometry, but what we are interested in here, and in computer science and especially machine learning, is to do the same with vectors which exist in dimensions that we cannot see. For example, we would be interested how to compute a length of a vector in 100-dimensional space. And you can say, wow, this is something complicated, but it's not really that complicated. So this is the same formula that we can use, and if you want to, you can see the formula here, yeah? Square root of the first component, x, and the second component, y. But the same thing applies to 3-dimensional vectors. So if in general, if I want to say what is the vector's length, if the vector is a, I can just put these two lines, and this means length, yeah? So if I want to if I want to look for the length of E, which is this 3-dimensional vector, if you remember, this one, 2, 3, 5. What I need to do is simply find the same square root and say 2 squared plus 3 squared plus 5 squared. And then you compute it and you get the result that the length is 616. But most interesting part here is now that we can apply this to a vector in 100-dimensional space. So let's define a vector f, which is in 100-dimensional space. And then first coordinate is 2, 1, 3, and then 96 more and 8, yeah? So 100 numbers. Interesting thing is to compute the length of f. We can just do the same. We can just make this square root. We can say 2 squared plus 1 squared plus 3 squared plus whatever plus 8 squared. And you get a length of something in 100 dimensions, which is really not intuitive when you think about it. But you can see that this operation, if we think about vectors as a list of some numbers, then this thing kind of scales with it. So the operations are very similar, no matter if you're in 2 dimensions or in 100 dimensions. And if you want to use Python to compute the length of this vector A, you can use this function called lineal norm. It doesn't even matter, you don't have to remember it. And you can use this function and it tells you, okay, the length of E is 6.16. And it works with the same way. If you have a vector of 100 dimensions or 3, it will just give you the length. Okay, now we have vector operations. So the idea of vector operations is, for example, you know what's 1 plus 1, what's 5 minus 3, what's 6 times 4, what's 9 divided by 3. These are the elementary arithmetic operations. And in linear algebra, we need to see how we can do something with these vectors, how we can add them, subtract them, and why would that be even useful. But what you might notice here is that a lot of operations in arithmetics can be seen on a number line. For example, this is number 1, and then this is number 3. And if you want to add 1 to 1 and 3, you just take this 3, you just take this length of 3, yeah, and take this length of 1 and add them together, so put 1 after 3, and you get, without much surprise, you get 4, because this plus this then ends up here. The thing is that in vectors things work in the similar way. So you have 2 x's, and if you have one vector here and one vector here, maybe this is not the best drawn, this and this, then you have projections on the x-axis and projections on the y-axis, yeah, for both of them. And then the same thing we have applied here we can apply here as well. So if you want to add these two vectors, you add this projection in x and this projection in y. You end up somewhere here. In the other direction, you add this. Actually, you subtract this from this. So then you cut it here. And then you get a vector, which is a plus b. Okay. So you can add them by adding this component. So this is now very similar to arithmetics, but in geometric terms, what we can do is we can add vectors by moving them around. For example, if we take the tail, sorry. We take the tail of the vector b and we slide it across the vector a, and where it ends, this is the vector a plus b. But we can do the other way around. We can slide the vector a across the vector b, and it will be ending up at the same point. And this just means that a plus b is equal to b plus a in the world of vectors. Another interesting thing is, imagine now we have a line. We have a line, and we have some vector on this line. As I showed you, vectors can be moved around, yeah? If we want to measure them, we put them in the coordinate origin, but we can, in principle, move them around. And so we have this vector here, and this is called, for example, a. And then we have some number, p, and we are interested in p times a. So p is just a number, so if this is a number line, so p can go b1, p can be 2, so we can move p around, yeah? So what happens is that when we add two vectors together, when we multiply vector with a normal number, with a scalar, we kind of change the length. So if we say 2 times a, we extend this vector, it becomes twice as long. When we multiply it, so we say minus 1 times a, the vector stays on the same line, but changes direction. So then it becomes this one. Okay, maybe I exaggerated it a little bit. If I say negative 2a, then it will be the same length as this one here, but it will be in the different direction. So as you can see, by multiplying a vector with a certain number, you can extend it indefinitely in each direction, but it must stay on the line, yeah? And this is what I made here. So we have here vector u and the number a, and we change the a, and then we can reach any point of this line, on this line. So this line is infinite in 2D here, and by multiplying a vector by number, you can reach anything. This is the first step. Okay. Vector subtraction. Now when we know what vector addition is about, like how we add these vectors, we slide b over on top of a. Vector subtraction is also very similar. There's nothing more to say about it. So we can say that a plus b, a minus b, sorry, a minus b, just like in mathematics, you can say 1 minus, actually, let me not say 1 minus. 3 minus 2 is the same as 3 plus minus 1 times 2. Yeah, so it's 3, then minus 2 equals 1. So you can, by changing the second number, or first, depending on what you want, you can translate what is addition into subtraction. And this is what we do here. But what we know here is that when we multiply by negative number, as we've seen here, we will change the direction of the vector. So it will go into the opposite direction. So when we do that, we simply need to change the direction of b and then add them together, just like we added before, slide b over a, and then you get a minus b. So this is how we do it in terms of geometry. But numerically, what we do is we simply add and subtract vector coordinates. So if the first vector is 3 and 4, second vector is 2 and negative 1, we simply add these projections, and you get 3 plus 2, 4 minus 1, and you get a plus b. You realize that it's 5 and 3. So this is x, and this is y coordinate. To multiply it by a scalar is also incredibly simple when using numbers. I just want to show you that using numbers, it really makes this very easy. We simply multiply each coordinate by, for example, 3, and we get, instead of 3 and 4, we get 9 and 12. If we subtract them, it is the same operation. You can just see subtraction as combination of addition and multiplication with -1, and that's the same. Here should be a minus b. This is a mistake. Simple. But then there are some other operations. For example, vector dot product, which are a little bit specific for the world of vectors, not really the same as something we have with numbers. And I don't want to go into details here. I don't want to bother you with details. But vector product is something useful. I just want to show you how something useful can work from the perspective of, for example, geometry and the perspective of calculus with numbers. So if we see how, if you open Wikipedia and see what is a vector dot product, they tell you it's a product of vectors' lengths and the cosine of angle between them. For example, here is the length of A, so for example 5, length of B is 2.24, and cosine of angle, I don't know, angle is 47 degrees, cosine will be some number. So the interesting thing to, not interesting, but the thing to note is that all three of these things are scalar quantities. They're just numbers. So this is 5, this is 2, and this is going to be something in between -1 and 1. So when you multiply three numbers together, you still get a simple number. So we are interested how to compute this single number of any two vectors. As you can see, if you want to do it geometrically, it's quite complicated. You need to find their lengths, you need to find the angle, you need to find the cosine of the angle. It sounds very complicated to do it. But vector product, this dot product, is kind of a very useful thing. For example, you can use it to find an angle between vectors. You can do it, for example, if you have one vector here and another vector here, you can use the dot product to find the projection of this vector on this one. Or for the same two vectors, you can use it to find the projection of this vector on it. But we won't go there. This is not our interest. Our interest is, how do we compute, for example, this dot product? I will later show you how we can use it. But it's incredibly simple to do that. So our vectors A and B are here. And to compute it, the only thing we do, we multiply the respective coordinates and add them together. So if we have 3, 4, and 2, -1, we multiply 3 times 2, we multiply 4 and -1, and we add them. So this is going to be 6, this is going to be -4, 6 minus 4 is 2. So as you can see, this kind of relatively complex thing in geometry becomes incredibly easy to do with just dealing with numbers, with dealing with vectors. This is how it is described. But then there is another thing. Now we are trying to connect it with things we have already seen. The question is, can we use this operation of a dot product somewhere else? Can you recognize it somewhere else? And the interesting thing is, yes, we can. For example, look here. This is vector E. This is the length of vector E. And what we did to find its length, we squared the coordinates and took the square root. Yeah? It's the same thing that we did with this vector. Yeah? So maybe I should draw this one again. Oops. I cannot just copy it like before. Okay, doesn't matter, I'll draw it again. You know what it is, it's just vector which is 3 and 4. And then to find the length, so this is A. To find the length of A, we said it's equal to square root of 3 squared plus 4 squared. Now the question is, can we use the dot product of the vector? So what the dot product does is multiply the x coordinate of the vectors, multiply the y coordinates of the vectors and all the remaining coordinates, and then adds them together. So what we have here, we have something multiplied by something, something multiplied by something, and something added together. So what we can do is, if the a is equal to 3 and 4, we can simply do the dot product between a and itself. So we can say 3, 4, dot 3, 4. So what we will have is 3 times 3 plus 4 times 4. As you can see, dot product is a very useful thing. It exists even in Pythagorean theorem. It can be used to formulate it. So if you want to define length of a vector, it's very easy to do it in terms of dot product. So instead of saying, for example, instead of writing 3 squared plus 4 squared, we can just do the same with the square root of a dot a. So just multiply the vector by itself and take the square root, and that's it. So this is one thing which is kind of useful about it. There will be more. The same is in 3 dimensions. So 3, 2, 3, 5, 2, 3, 5, you multiply, you add them together, and you get the length. To do this by using code is very simple. We simply need to learn very few functions. For example, to add them, a plus b, you just type a plus b in Python. It cannot be simpler. If you do print, then you get rid of this array. So just to make it nicer. Or a minus b. So the thing is, in order to be able to multiply, to add or subtract vectors, they need to be of the same size. So if a is, I don't know, 3 and 4, and b is 2 and minus 1, we can add them because we can add 2 and 3 and 4 and 1. But if e is 2, 3, 5, we cannot add a plus e because we would add something which lives in a completely different world. So vector 3, 4 lives in 2D, lives in a plane, and vector 2, 3, 5 lives in 3D. So we cannot add them together. They are completely live in different worlds. So what we can think is, for example, we can add a 0 here to 3, 4, and then they are the same size. But the thing is, this really is not allowed, because if we do this, we are not having the vector a again. Vector a is specific because it's two-dimensional. If it adds 0, it becomes a completely new vector in a different space. It's like one thing translates from one space into another. It's literally changing space. So if we add a 0, this will no longer be vector a. This is important to notice. So to add vectors, to subtract them, they need to be of the same size. So if I say a plus e, not work. A plus b works. A negative b, a minus b works. If we multiply it by 5, you just say 5 times a, 5 star a, it works. Now the question is, if we say a times b, so this is something which makes a lot of sense, but in mathematics we do not really learn about it. If we say a times b, what happens is two coordinates get multiplied together. For example, if we had here actually we see what a is already, I have to draw it, but if I say it here, a times b, and if I type this in my computer, what happens is the computer computes 3 times 2 is 6, 4 times negative 1 is minus 4, and it gives me a result, a times b is 6 and then minus 4. But this is not what we learn in math. In math we do not really learn this thing, although it's very useful in computer science, but because this kind of product is similar to addition. You need to have two vectors which are of the same size. In computer science, we learn, in mathematics in school, you learn, unfortunately, about different kind of products. But this product is also very useful. It's called the Hadamard product, and we write it like this, A, and then this weird circle, B. So if you see this, if you start, for example, learning about machine learning and open the book, you will see the equations, for example, of backpropagation, which is the algorithm of neural networks. And there will be so many of these kind of things. And you will think, oh man, I cannot deal with this. This is too complicated. I don't even know what the operations are. But the thing is, it's really super simple. It just means if you have two vectors of the same size, just multiply the components element-wise. 2 times 2, 3, and 4 times -1. So it's very simple. Okay, now let's go back to this dot product. So that product means you have two vectors of the same size, you multiply components together and then add them. So you can see that here we have multiplying the components, we remain with multiply components, and the only thing which is different with the dot product that we showed before is that we need to somehow add these two things. So that product means do the same, multiply the components, but then add them together. So to achieve this, we can use the function sum. So in order to find a dot product, first part of the dot product, we do the Hadamard product of A and B. So we just multiply first x by x, y by y, and then sum, this is the function in Python, which just adds all the elements in a vector, it just adds them together. So 6 and -4, it will add it to 2, and the result will be 2. Yeah. In this way, you can use Hadamard product and a sum and a square root to find the length of a vector. Before, we'd use this formula. Where was it? This lineal norm to find the length of a vector. But now, once we know what's going on, you can also construct this formula yourself. You can just say, I make a Hadamard product of the vector by itself, I sum them, so this is x times x squared, plus y times y squared, then I sum them, which is x squared plus y squared, and then I take a square root, and I get the length. So super easy. Okay. Need to put shades a little bit down. Mm-hmm. No, but that's not what I want. Okay. Okay. Now, when you start working with numbers and when you start programming, you realize that not all numbers are equal. And I'm not now speaking only about numbers like pi or e or, just some normal numbers are quite funny, quite interesting. And even if you think about them geometrically, for example, you have here a number line. You have 0, and you realize, you have some numbers. You have, for example, 1, 2. You add anything you add 1, for example, to 2, it jumps here, it becomes 3. You add -1, it jumps left. So somehow some kind of operation is associated with it. But then also, you have any number, you multiply it by 0, poof, it goes back to 0. Yeah? You add 0, the element doesn't change. Or you take, for example, this 3, multiply it by -1, and you get jumps here to -3. You multiply 2 by -1 and jumps here. So there are some kind of certain operations that these very elementary numbers like 0, 1, and -1 can do that are quite significant. And the question is there something similar going on in the world of vectors? And my answer is yes. There are certain vectors which are similar to these numbers, but they play a role in the world of vectors. What is interesting about them is that they exist in each of the axes of the space. For example, this is x-axis, and x-axis has something which is very similar to the number 1 in arithmetics. And this is this thing which is called I. This is called a basis vector. It is the vector which is parallel with the axis itself and which starts at 0. And its length is 1. And then you have another vector called j. It goes into this direction, and it's also of length 1. And they're kind of special. Why they are interesting is that you can use these two vectors to construct any other vector in this space. So they're called basis vectors. Let me explain what I want, what I would like to say here. For example, the coordinate of I, in terms of this representation, would be, so x is 1 and y is 0 because it's on the x-axis. So the coordinate is 1, 0. And the coordinate of j, which points up, so x coordinate is 0, but the y coordinate is 1. Yeah? Okay, let's just keep this in mind for now. Interesting thing is, how can we use this I and j to represent this vector? Well, what we can do is we can take 3 i's, projection of 3 i's, add them together. So add 3 i's together, add 3 j's together, and then they will together make this vector. They will be their projections. It's literally, they will form its coordinates. So yeah, you create vector coordinates by adding i's and j's. So this is an interesting thing, how we can really transform the vectors. But there's another thing. This vector does not need to be represented with these numbers like 3 and 4. It can go, for example, here, its coordinate can be 2.18 and negative 1.03. Yeah. So what you do, you have these, you have this one, which is I. We call it I hat. It has this thing on top. That's the name in English. We have this one, which is called j hat. And now, remember this picture. Remember we had a vector? Oh, I lose it every time. Here. Remember this vector? We just take a vector, multiply it by some number, and then we can represent anything on this line. Yeah, just multiplying with the correct number. It can be positive or negative if you want to switch direction. So what we can do here is we can just take I, multiply it with some number, and if you multiply it with, for example, with 2, then you get here. Yeah, this is 2i from here to here. But then if you multiply it by negative 2.18, sorry, this is a mistake. This coordinate is negative 2.18. Of course, it goes to the left. So what we can do is we can stretch I multiplied by a negative 218. It becomes this. Take the other vector, multiplied negative 1 over 3. It comes here. And then you represent this vector with this I and j. So they become some basic units that you can multiply with some number, and you can reach any vector. And as you can see here, I can now rewrite these vectors. For example, A, which was 3 and 4, I can now rewrote it as an equation which says A is equal to 3i plus 4j. The second vector was negative 2 and 1. We can represent it as negative 2i plus 1j. So we can represent all of these vectors, which is with this expression, which is called a linear combination of vectors. So we combine something which goes in one direction along one vector, and with something which goes to another vector, we add them, and then we recreate the original vector. You see, we can do the same in 3D. We can use now I hat, j hat, and k hat, which is the third one, which goes into z direction, and we write E is equal to 2 times I hat plus 3 times j hat plus 5 times k hat. And the same thing can be done in any number of dimensions. It can be done in 3 dimensions, or it can be done in 100 dimensions. So this is why these elements are very important, this I, j, and k. Okay. Later, what I want to show you, we now have a break. Later, I will continue. There's still a little bit more to say about this. Okay, so then we have a break now.